Hi, I'm Sotiris Apostolakis, a fifth-year PhD student from Princeton University, and in this video I'll present the ASPLOS' 2020 paper titled Perspective, a sensible approach to speculative automatic parallelization. This is joint work with Ziyang and Greg from Princeton, Professor Campanoni from Northwestern, and my advisor David August. Let me start by motivating automatic parallelization. Since their inception, multi-core processors have been grossly underutilized. Even until recently, Google reported around 30% average core utilization in its data centers, while Twitter had less than 20%. This underutilization has driven up costs, hurt the environment, and even stunted the growth of multi-core technology itself. A major reason for this underutilization is the difficulty of extracting parallelism fine-grained enough for multi-core. Despite many new tools, languages and libraries for parallelization, programmers are mostly limited to coarse-grained forms of parallelism, such as job or data parallelism. This coarse-grained parallelism, though, is ill-suited for multi-core, as it tends to stress shared resources, such as caches and memory bandwidth. Automatic parallelization, on the other hand, has the potential of enabling efficient use of multi-core systems without undue programmer effort. With automatic parallelization, the programmer writes sequential code, and then the compiler automatically produces an executable that runs efficiently in multiple cores. The next question is why we focused on speculative automatic parallelization. For a long time, parallelizing compilers exclusively relied on statically proven properties by memory analysis, and as a result, they had limited applicability. Memory analysis is fundamentally limited in theory, since for any fixed analysis algorithm, there is always a counterexample input for which the algorithm is imprecise. Memory analysis is also insufficiently precise in practice, especially for languages like C and C++. But even if analysis was precise enough, still it would have to conservatively respect all possible inputs, even though there are cases where real dependencies rarely manifest and thus could be ignored. Such cases are, for example, error conditions for multiple inputs. Following the success of speculation for extracting ILP, speculation in TLP, thread-level parallelism, gained traction and overcame the applicability limitations of memory analysis by enabling optimization of the expected case. I will now describe the state-of-the-art approach for speculative automatic parallelization, and then I will discuss its core inefficiencies to motivate our work. Next, I will present our approach, proceed with evaluation results, and finally conclude my talk. Parallelizing compilers start with the sequential code and use static analysis to analyze the dependencies among program operations. The hardest part of static analysis is memory analysis, which analyzes memory accesses. Then parallelizing compilers apply a sequence of enabling transforms to make the program more amenable to parallelization. Examples include speculative privatization, reduction, memory speculation, and control speculation. After the application of enablers, the program is parallelized, if possible. Many parallelization patterns exist, but the most desirable and simple is dual, the independent execution of loop iterations. Other patterns like Helix or PSTWP are less efficient but more applicable. Our work targeted dual, and thus I will only talk about dual parallelism in this talk. Overall, automatic parallelization is all about handling dependencies. Analysis disproves the existence of dependencies, enablers break dependencies but with a cost, and parallelization techniques try to tolerate unremovable dependencies. All these advancements in compiler research have increased considerably the applicability of automatic parallelization. However, speculation-based enablers have also created profitability problems. Breaking dependencies with speculation has introduced costs that often negate the benefits of parallelization. Our work focuses on mitigating these costs and enabling efficient speculative parallelization. We use Privateer as the state-of-the-art baseline system for this work. Privateer, published in PLDI 2012, is a speculative dual parallelization system with the highest applicability. We explored its overheads and identified two main inefficiencies. The first one is excessive use of memory speculation. Memory speculation asserts absence of dependencies not manifested during profiling, and it's very expensive to validate due to costly communication and bookkeeping costs for every single speculated dependence. This is by far the most common inefficiency among all prior speculative systems. The second inefficiency is expensive speculative privatization, which involves monitoring of large write sets to correctly merge the private memory state of parallel workers. Same as Privateer, other speculative systems with privatization support suffer from this overhead. Next, I'll present an example that illustrates these two inefficiencies. This example is taken from the Dijkstra benchmark, from eBench, a benchmark used in the evaluation of Privateer, our baseline system. Here, we have a part of a simple for loop. We have a heavily biased branch that in practice is always taken, even though we cannot prove it statically. We also write and read a memory object using pointer PTR, which is not modified within the loop. Now the question is how a state-of-the-art system would parallelize this loop. As I said before, it's all about handling dependencies. Therefore, we focus on the program dependence graph, the PDG. We start with the conservative view of the PDG for these two instructions, with anti-dependencies omitted. To better understand these dependencies, observe here two dynamic instances of these instructions for iterations k and j, and you can see the two cross-iteration memory dependencies and the intra-iteration one. The goal here is to remove all the cross-iteration dependencies, namely dependencies that prevent dual parallelism, the independent execution of loop iterations. Now we follow the state-of-the-art approach of trying one thing after the other to simplify this PDG. First, static analysis tries to disprove these dependencies, but to no avail. Then we start applying enablers. Control speculation has no effect since it's only applicable to speculatively dead code. Yet, memory speculation asserts that there is no cross-iteration data flow from instruction I1 to I2 simply because this flow was never observed during profiling. Finally, the outward dependence can be removed with the application of speculative privatization, which creates private copies of the underlying memory object for each worker. At the end, we manage to remove all cross-iteration dependencies, and the loop can now be parallelized with dual. But in this process, expensive to validate memory speculation was used. Now let's see why memory speculation validation is so expensive. The problem is that every worker needs to record and communicate its access pattern so that an overlap is detected. The monitoring operations are depicted here in gray. Let's go through a simple timeline for this example to demonstrate how validation works. We have two worker threads that execute the loop and a validator thread that checks their access pattern. Worker 1 executes the first iteration and monitors the two memory axes and notifies the validator thread that it wrote at the memory location pointed by PTR. Worker 2 does the same for iteration 2. Then in iteration 3, let's say that the branch happens not to be taken. In this case, worker 1 read a value that was written in a previous iteration, which violates the speculative assertion that this cross-iteration data flow cannot occur, and thus it causes a misspeculation. But even without misspeculation, which in fact never happens for this example, workers still perform a lot of additional work, significantly decreasing the profitability of parallelization. Now let's assume that the branch condition in our example is statically proven true, and let's parallelize this loop again. Same as before, we start with a conservative PDG and we try to simplify it. Static analysis is able this time to remove the cross-iteration data flow from I1 to I2, since I1 executes on every iteration, and thus it kills the data flow from previous iteration. Then again, speculative privatization resolves the output dependence. Speculation was used to infer the underlying memory object that was privatized. Here, we enable parallelization without using memory speculation, but still, speculative privatization turns out to be expensive for prior systems like Privateer. Workers still have to use write monitoring to know in which iteration every byte was last written, and report that so that the live-out state is computed correctly. Here we avoid the read monitoring, but we still have write monitoring. Going through the timeline again, worker 1 executes the first iteration and also records the written memory locations. Then everyone does the same for every iteration, and at the end, everyone communicates the private copy of the privatized object along with the timestamp. And the master thread, which continues execution after the parallel evocation, keeps the latest one as live out. In this case, the object from worker 1. Thus, even with just privatization, the overheads can still get pretty high. Just to quantify the two overheads I just described, Privateer had to monitor for the Dijkstra benchmark more than 1 terabyte of reads and writes to validate memory speculation and perform privatization for an input graph of 3000 nodes. These numbers are huge since a lot of monitoring occurs in an innermost loop. In our work, we dramatically reduce these numbers. I'll proceed with our approach, the perspective approach. Overall, the goal of our work is to maintain the applicability of prior speculative automatic parallelization systems without the unnecessary overheads of prior work. Before I describe our approach, let's go back to the original example and see intuitively how we can parallelize the loop more efficiently. Memory speculation used by prior work in this example requires heavy monitoring, and this because it just asserts the absence of non-observed during profiling dependencies, without any understanding why they are not observed. There's no reasoning. In this example, the actual reason why the cross-iteration data flow from I1 to I2 is not observed is because the branch is always taken. However, the speculative assertion that the branch is always taken is only known to control speculation, which can only reason about speculatively dead code, and no other compiler component becomes aware of this speculative control flow information. So this information ends up being wasted. The solution is to make memory analysis aware of this speculative assertion. Since control speculation will validate it, memory analysis can treat it as a fact, ignoring the possibility of misspeculation. By doing so, memory analysis can view I1 as executing on every iteration, and thus it can infer that I1 kills the cross-iteration data flow. In terms of the cross-iteration output dependence, we can avoid write monitoring by having a privatization variant that understands that the privatizable memory object here is overwritten at every iteration, and thus the live-out state is the last iteration state. For such a variant though to be applicable in this example, awareness of the biased branch is also necessary. In the end, by fully leveraging an inexpensive to validate speculative assertion, we can efficiently break all cross-iteration dependencies without the monitoring of prior work. To validate the speculative assertion, we only need to check for control misspeculation, which practically adds zero validation overhead. Using these observations, we redesign the compiler to automatically find these opportunities. The high-level goals of our approach are to increase awareness within the compiler of what every component is capable of, enable collaboration to maximize the effect of speculative assertions, and avoid any unnecessary transformations, especially expensive ones. The perspective approach involves three main contributions. First, unlike prior work that applies a fixed sequence of enabling transforms, we propose a more sensible approach, where we plan first before applying any transformation. The key insight here is that the effect of parallelization enabling transforms is predictable and easily expressible on the PDG. In the perspective approach, we start with static analysis that produces an initial version of the PDG. Then, each enabling transformation expresses on the PDG which dependencies it can handle along with an estimated cost. Then, the transform selector examines all the options and picks the cheapest set of enabling transforms that covers all the dependencies that need to be removed for dual parallelism to be applicable, namely all the cross-iteration dependencies. Finally, only the selected transformations are applied. The second contribution is a speculation-aware memory analysis. In prior systems, profile-based speculative assertions are used separately from memory analysis. Instead, in this work, memory analysis is made aware of these speculative assertions, effectively computing their full effect. And this often results in new cheap alternatives for breaking dependencies. Additionally, in this design, enablers such as privatization, instead of operating in isolation, also become aware of these speculative assertions. This creates an opportunity for new efficient enabling transforms that leverage all this exposed information. In fact, Perspective introduced new efficient variants of speculative privatization that avoid the right monitoring of prior work. For instance, I briefly presented in the example earlier a privatization variant that leveraged a control speculation assertion to show that the privatizable memory object is overwritten at every iteration. Another example is a variant that leverages value prediction assertions to predict the live-out state instead of monitoring it. To recap our motivating example, Perspective, as opposed to the state-of-the-art, avoids for the Dijkstra benchmark use of memory speculation and expensive privatization, and thus almost eliminates, as you can see, privateer's memory access monitoring. The effect in terms of performance is 4.8x speedup over privateer for this benchmark. Note that Dijkstra was in fact the motivating benchmark for the privateer paper, which makes this dramatic speedup even more impressive. The Perspective framework is implemented on the LLVM compiler infrastructure, and it includes a set of profilers, a parallelizing compiler, and a lightweight process-based runtime system. The framework consists of around 80,000 lines of C and C++ code. The compiler workflow is depicted on the right. For explanation of this workflow and for implementation details, please refer to the paper. Let's now see some evaluation results. Perspective is evaluated on a commodity shared memory machine with 28 cores. The claim that's empirically evaluated is that we maintain the applicability of prior automatic dual systems while improving their efficiency. In order to avoid cherry-picking and validate our claim, the evaluated benchmarks cover all the parallelizable benchmarks from two state-of-the-art automatic parallelization papers. Benchmarks are from SpecCPU, Parsec, Polybench, and mid-bench suites. This graph shows fully automatic whole program speedup over sequential execution across various number of cores for 12 C++ benchmarks on a 28-core machine. As you can see, Perspective achieves scalable performance, in most cases linear speedup, thanks to the elimination of the overheads we discussed. Alvin exhibits smaller speedup, mostly because the parallelized hot loop covers a smaller part of the whole program compared to other benchmarks. In this graph, we compare Perspective against privateer of prior work, and we show speedups over sequential execution on 28 cores. The main takeaway is that Perspective doubles the geomean performance of privateer. The reason behind this big performance improvement is the dramatic reduction of the monitored reads and writes for speculation validation and privatization, as seen in this table. For more evaluation results, including breakdown of the benefit of each contribution and the effect of misspeculation, please refer to the paper. To conclude, this work represents an important advance in fulfilling the promise of automatic parallelization. We identified and mitigated core inefficiencies of prior speculative parallelization systems with the introduction of a speculation-aware memory analysis, new efficient enabling transforms, and a new compiler design that enables careful planning. The end result is scalable speedups and doubling the performance of a state-of-the-art system. Finally, this paper has gone through the artifact evaluation process and was awarded all the available badges. The artifact is publicly available and can be used to reproduce the main evaluation results and corroborate the claims of this paper. Thank you.